Today we're going to talk about exponential functions. And so we have an exponential function when you have a base a and you're raising it to the x power. And so your x value is the exponent in the function and your y value is that f of x. So in example number 1, we're going to sketch these two graphs on the same coordinate plane to see how they compare. And so the easiest way to sketch a graph of an exponential function is to make your t-chart. And so we have x and f of x. And if we plug in -2, that would be 6 to the -2. And so remember that a negative exponent means that you're going to make it a fraction. So it's 1 over 6 squared, which is 36. Then we can plug in -1. So it's 6 to the -1, which is going to make it 1/6. We can plug in 0. And any number to the power of 0 is going to be 1. If we plug in 1, we get 6 to the first, which is 6. And if we plug in 2, we get 6 squared, which is 36. Okay, so now let's make our t-chart for the other function, g of x equals 12 to the x. And again, we're going to make our t-chart. And so we're going to plug in the same numbers, so -2. When we plug that in, 12 squared is 144, but because it's negative, it becomes a fraction, 1 over 144. And then we plug in -1. 12 to the -1 is 1 over 12. Plug in 0, anything to the power of 0 is 1. If we plug in 1, we get 12 to the first, so that's 12. And if we plug in 2, we get 12 squared, which is 144. So now this gives us an idea as to what our units should be when we go to graph it. So looking at our x values, we can go with units of 1. So we're going to make each one of these lines 1 unit. And then we can look at our f of x or g of x, our y values, and see what we've got going on here. So we've got some fractions, they're positive. And then we go up to 144. So we might not want to graph that point because that's going to be a lot. But so we can go up to around the 12. So looking at how many lines we have here, we can make these units of 2. In order to keep the graph a little less messy, I'm going to label every unit of 10. So I'm going to count up 5 lines. So 2, 4, 6, 8, 10. And then 2, 4, 6, 8, 10, so that gives me 20. Okay, so now I can go ahead and graph because I can figure out where some of these points are going to go. And so we've got -2 and 1 over 36, so that's going to be like really close to your x-axis, not quite on it, but very, very close. -1, again, is going to be very, very close to that x-axis. And so we can plot that point, 0, 1. So that's going to be, remember that our lines are 2 for the y-axis. So we're going to go halfway in between. Then we have the point 1, 6. So we're going to go up 3 lines, because remember that every line is a 2. And then we have 2, 36. That's not actually going to fit on our graph, but we can kind of get an idea as to what our graph is going to look like. And so we're just going to try to connect these dots. And remember that we're not crossing over the 2 line, the line x equals 2, because we can't get up to the 36 on this graph. All right, so now let's go ahead and graph the g of x function. And let's go ahead and label this as f of x for the blue one. And now we're going to do we're going to graph our g of x function. Again, we have -2, positive 1 over 144, so that's very close to the x-axis. -1, 1/12, again, is also very close to that x-axis. They share the point 0, 1. Okay, and then we've got 1, 12, so at 1, we're going up to 12. So this one, and then the next one is going to be 2, 144, so we're not even going to get close to that. So this one is actually going to be quite a bit steeper than the other graph is going to be. And if we could zoom in on the graph, we would really see how they're separate. The higher up your x value goes, the farther apart your graphs are going to get. All right, so now let's take a look at example 2. This time it's just this similar graphs, but notice what's going on with the x here. We're multiplying that x by a -1, and if we think about our transformations, what that's going to do is that's going to reflect it over the y-axis, because remember, when you multiply the x value by a negative, that is a reflection over the y-axis. So when we write our t-chart, we're going to have very similar answers to the points that we had for the original f of x in example number 1. So when we plug in -2, we have two negatives, so 6 to the -2, that's just 6 squared, so we get 36. When we plug in -1, we get 6 to the -1, which is +1. We plug in 0, anything to the power of 0 is 1. 6 to the -1 is 1/6, and 6 to the -2 is 1/36. Then we can go ahead and draw up our t-chart for the g function. We'll use the same points, or the same x values, I should say. And so when we plug in -2, that's 12 to the -2, so that's 144. Plug in -1, 12 to the -1 is 12. 12 to the 0 is 1. 12 to the -1 is 1/12. And 12 to the -2 is 1/144. So we can see that we have similarities between our two graphs, so we're going to label them the same way. So each vertical line is going to be a 1, and each horizontal line is going to be 2. Okay, and so now we have the lines labeled, and so we can go ahead and graph our points. So we have -236, that's not going to fit on our graph, but we can graph -1/6, and the point 0, 1, and 1, 1/6, and 2, 1/36. And then we can sketch our graph. We're going to get very close to this. And I'm not very good at that, but you can see where we get close to that -3, but we don't actually touch it. And so my graph shouldn't really be touching it. But we're just sketching here. And so our g function, we've got -2, 144. That's not going to fit on our graph, but -112 will. So there's that point. We've got 0, 1, 1, 1/12. Again, that's going to be much steeper, but you can see where these two graphs are the reflection of the previous graphs. Okay, so one thing that we use quite often in exponential functions is this letter E, and that's called the natural base. And so a natural exponential function is f of x equals e to the x. And really what e is, it's an irrational number. So it goes on forever without repeating, just like pi. Pi stands for 3.14159 and so on. And so E represents this specific number. And we can represent it with an expression, we can approximate it really, with an expression that is 1 plus 1 over x to the power of x. And so that expression is going to approach E as your x value approaches infinity. So as you increase your x value, that expression is going to get closer and closer to the actual value of E. So we have some formulas here for computing compound interest. So we might need to use those later. But for example number 3, we're going to look at half-life. And so exponential functions are really useful when calculating half-lives and growth models. So in example 3, we're going to let Q represent the mass in grams of radium, whose half-life is 1,600 years. The mass of radium present after T years is given by Q equals 16 times the quantity of 1/2 to the power of T over 1,600. So what is the initial mass? So initial mass means that time is 0. So for our initial mass, T equals 0. So we're just going to plug that into the formula. So we have 0 divided by 1,600, which is just going to give you 0 as your exponent. So you really just have 16 times 1. So your initial mass is 16 grams. Now let's take a look at the second question. What is the mass after 1,000 years? So our T is going to equal 1,000. So in this case, we're going to plug in 1,000 for T. And this we can just plug into the calculator, and we end up with approximately 10.37 grams. So you can see that the mass of the radium has decayed over that 1,000 years. All right, let's take a look at a growth model. In example number 4, a city's population is growing at a rate of 8%. After T years, the population is given by P of T equals 450,000 times e to the power of 0.08 T. Notice that that 0.08 is the rate of growth. Okay, so we want to find the initial population. So again, T equals 0, so we're finding P of 0. So we have 450,000 times e to the power of 0.08 times 0. So really that e is to the power of 0, which makes it 1. So we have 450,000 people. So now we're going to find the population after 20 years. So we're plugging in 20. So 450,000 times e to the power of 0.08 times 20. So we're going to plug that all into the calculator. And remember that your exponent is the 0.08 times the 20. Okay? And so when we plug that in, we end up with our population is approximately 2,228,865 people. And typically when this is being reported, they'll just round it. They might say 2,229,000 as an approximation. So now we can go ahead and graph our function, and we can take a look at what kind of units we might want to use. But let's remember that this graph is talking about the city population. So we're going to title it with the city population. Our y-axis is going to represent the number of people. And our x-axis is going to represent the number of years. Okay, so we can, we're looking at from 0 to about 20 years. So we can make, along our x-axis, we can let each of those be a 2. So we got 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22. Okay, and so I just labeled every other line just to make it a little bit easier to read. Then we're going up to a little over 2 million. And so we can make each line on the y-axis 200,000. So that means every 5 lines is going to be a million. So 2, 4, 6, 8, a million. And then 2, 4, 6, 8, and then 2 million. All right. So now we can kind of get an idea as to what our units are going to be. So now we can graph those 2 points. So the initial population, and this is just the initial population of when they started monitoring. So the initial population, which would be the y-axis, is 450,000 people. And so that's going to be right about here, just above the 400,000 line or marker. And then when we plug in 20, after 20 years, it's a little more than 2,200,000. And so that's going to put us right around here. And so then we can take a look at, you could plug in 10 to kind of get an idea as to where that curve is going to go. And 10 ends up being, when you plug that in, just a little over 1 million. And so we can plot that point. And so we can add a little bit of curvature, and notice that you're never going to go across that x-axis. And so this is a sketch of the graph of this population function.